Okay.
Yeah. So
All right.
like we're broadcasting now. So basically, Nick, I don't know if you got the full like lowdown, but this basically is a place where like every e-NABLE student researcher who wants to can like showcase their designs, get feedback on it, and then hopefully we can like through the power of this community we can all improve on what we're working on.
Yeah, sure. Um, hmm. I'm away from what's currently my lab, aka the basement of the co-op I'm living in, because again, vacation. But I've been messing around with trying to do really cheap do-it-yourself fluid muscles that are aimed at being pretty weak, basically. So the norm with fluid muscle is a inflatable tube wrapped in basically a Chinese finger trap. So you put pressure in the tube inflates, the finger trap gets shorter with a whole bunch of force.
Mm-hmm.
And the norm, I suppose, is to use some pretty beefy rubber tubing. So you can't inflate it at all until you get like 1 bar or so above atmospheric. And then you start getting a lot more power than a regular piston, around 2 to 3 bar. But we don't need anywhere near that much power, and we don't want to play with that much pressure. So I've been fooling around with doing the same thing with basically balloon animal balloons instead of the thick rubber. And I can inflate it with almost no pressure, and there's a pretty direct relationship between how much pressure I put in and how much force I get out. I just got this working before my flight, so I haven't like actually measured things, but feels that way. So the hope is that I can use body power to compress one, and use that to contract another one to drive the hand. So probably a shoulder harness to one in the forearm for a transradial thing.
So this is a replacement for the whole.
It's a replacement for the bowden, essentially.
Okay.
I have a vision of a bagpiper with the bellows under his arm, but I'm assuming that's not what you're thinking of.
No, I'm thinking, so if you pull on one of these muscles, it's going to pressurize the water, right? I mean,
sure.
If you've got it full of water and you pull on it, it'll pressure. So I'm thinking I'll just put maybe 2 or 3 of them in parallel on the back, so you use the same sort of harness as you would for a bowden, except to pressurize water.
So is the reason... Go ahead, sorry.
So the 2 motivations are mechanical efficiency. I'm hoping this is more efficient than a little cable through a tube, and in the future, flexibility. So I can imagine it'd be pretty easy to have multiple driven muscles and just switch where the water goes, and then do different things, which seems easier to me than a mechanical switch.
Why do they traditionally use the thicker tubing? I would think the only reason I can think of would be sort of resilience and robustness.
Yeah.
And so I guess my only concern is that we're going to pop our balloon animals quickly. It's a really cool idea.
Mm-hmm. Yeah. So the typical application for these muscles is the Atlas robots. They don't get used much for whatever reason. Well, part of it is that they don't provide you with linearity like you get out of a piston, and they're a lot harder to control than a piston if you're trying to get partial drive. But if you just want all or nothing like I think we do, then it's not bad. But they're usually for much more high power applications than grabbing something, is I think the main motivation for those really thick walls. But if balloon animals turn out too weak, I think there's still a middle ground.
Why is this better than pistons? Is it just basically the manufacturability of it?
Manufacturability, and it weighs a whole lot less, and it's soft. So if in the future, my mad dream is to be able to make like a whole prosthesis cast in silicone and just make it look photoreal, because you can do silicone like special effects makeup right on top of the stuff.
Right.
Yeah.
Which is a rather silly goal, but you can put
one
of these inside of.
Go Go ahead. No, sorry. Go ahead.
Go ahead.
No, I was gonna say the soft is pretty cool. So there you go. Sorry. The soft is pretty cool. I like the soft. I think the one thing when we were looking at using piston-driven systems last summer, we talked with a company that makes hydraulic bike brakes, and they said they just 3D print their models anyway. They said they would 3D print models out of ABS, acetone vapor treat, so that they get a smooth bore, reasonably smooth bore, and they could do tests on their hydraulics, on their hydraulic assemblies. So I guess I would say that I think it's totally feasible to do a more traditional hydraulic piston system using a fully 3D printed implementation. But I like the idea of that photorealistic, being able to sort of just directly mimic and print. I think that's a really cool direction to go that enables.
Yeah, so the mad dream in the distant future is to just go like, there's a muscle here, there's a muscle in my thing. And not going to happen because that would take a lot of valves, and valves aren't cheap. But it would be very cool to be able to do.
Well, then the problem is to create a 3D printed valve.
Yeah, well. And, I will try because this is all reasonably low pressure, especially if we're talking about body power, so I don't know. Maybe we can get away with it. That'd be nice. There's some background noise. What were you saying?
Okay, Adam, we're going to unmute you. There you go.
Is this a hydraulic system?
Yeah, water, not air.
Okay.
And Nick, are you doing this? Are you doing this research with a research lab back at?
No, I'm just doing it myself. I might. So Professor Lipson left Cornell after this semester. He's moving to Columbia University. Yeah.
Oh.
Yeah, interesting. But so there's Professor Rob Shepard that does soft robotic, pneumatically actuated stuff a lot. So if I get this to the point where it's reasonably interesting this summer, I'll probably just take this hand to him and be like, can I work on this in your lab? I probably don't need funding. And I can't imagine the answer to that is no. And he's also good friends with Professor Lipson, so I can have Hod recommend me. And other than that, not really. It's independent.
Okay, that sounds good.
That's awesome. Yeah.
Are you posting designs anywhere for this, or is it just?
That thing, the fluid muscle, I seriously got working 11 p.m. the night before my flight, so I haven't posted that yet. The other thing I'm playing with this summer is just a silicone cast hand.
Yeah.
So printing a skeleton with ligaments and doing that. I was talking about this at Amory last summer, but what I stumbled into was that the tendons get stuck in the silicone. So the scheme this time around is to put the tendons in, again, balloon animal balloons, and either just leave them like that and see if that's enough, or potentially inflate them slightly so you get little bubbles of balloon at each joint to leave a little bit of clearance for that that tendon path to pop out away from the skeleton. And as to the why question, because the first question is why am I spending so much on this smooth-on silicone? It's the closest thing I've heard of to flesh material, which is obviously a nice perk. It's machine washable. It's repairable very easily, which is something that Peregrine was complaining about with gripping materials. So I'm gonna print a mold for this silicone hand, and once you've got this hand, I think you'll be able to just mix up a bit more silicone, put it in that mold, put the hand back in with it, and you'll heal any cuts and scrapes over a few hours. And then again, I go back to you can do makeup on these things and make them photoreal, which would be nice.
Going back to your tendons sticking in the silicone, do you think you could just glop them up with petroleum jelly or something like that? Basically, coat them with something so that that wouldn't adhere or cure to the control lines.
It wasn't actually adhesion that was getting me. The first test I did was I just mixed up some silicone in a cup, threw some string in, and pulled it back and forth through that, and it was really smooth, not much worse than going through like PLA would be. The trouble is that you have the silicone conformed right onto the string, so when you try and shorten that path of string,
I see our Helena down there.
So it's not hard to push rubber out of the way, or push silicone out of the way, but compressing it significantly is incredibly hard, and the silicone immediately touching the rubber would have to compress axially along the string, and that's what was killing me.
Okay. So, like, have you explored a pneumatic system instead of using a hydraulic one?
I haven't, but I think in general, air pressure is kind of harder to make and maintain.
Mm-hmm.
So, I don't know.
Yeah.
It might be a way to do it. I like using water for this because it seems like a nice, simple, closed kind of direct system between. I don't know. So the nice thing about air muscles that kind of makes them see a lot of use in bipedal robots and the like is that they are dynamic and they have some like give to them. And maybe that's something we want. I don't really know, but I don't think we can body power pneumatics. It doesn't seem intuitively doable to me. Certainly worth trying, though.
Okay. I also saw you posted a link about like a finger design that you was one piece, and then you said, could you elaborate on that a bit more?
Yeah. So that's also just biomimicry, more or less for its own sake. Well, it does have some nice benefits. So instead of, I think Adam's talking to us. Has to drop. He'll be back next week. Oh, is this weekly? Awesome. Yeah. I'll normally be at work at this hour, but I guess I can take late lunch. What was I saying? Oh, so what was I saying? Oh, right. So essentially, I just print a cylinder sort of thing and a cup that goes against it so that they can slide like that. And then I just have a hole through the cylinder and a hole behind the cup thing, and I tie them together with string. And the kind of motivation there is, first of all, I think that'll work better inside of silicone than the screw in a hole. I don't think it'll get stuck as much. I'm hopeful. I may end up just having to put the whole skeleton inside of a glove before I do silicone. That might be the answer, but we'll see. But the other thing is, outside of the whole let's wrap it all in silicone thing, it's a lot easier to print those joints than it is to print the hole in this thing. I mean, it's way, way easier to make big, smooth arcs than tiny, dimensionally accurate and smooth holes and pins.
Right.
And let's see, other thing. Oh, it's just nice to not have to buy screws. I mean, just use string.
Yeah.
Yeah. The only downside is that it takes a long time to put together because I need to try. Well, okay, so. The issue, like the failing with it is you need to get the string tight enough that you can't wobble this joint sideways because that'd suck. So when I was trying to get our usual, I guess it's like 1.2 millimeter white shade cord stuff to do this, the minimum bending radius on that string was just too big. I couldn't tie it tight enough. And I probably could have like rounded the parts to make that workable, but that sounded meh. So what I ended up using was this sort of heavyweight thread, and I just did like 8 or 9 loops of it through each joint, and that works great. It's perfectly tight. It doesn't loosen at all when I try to load on it until it breaks completely. It's really awesome. The only problem is you have to run this thread through each joint 8 or 9 times. So it takes like 5 minutes for each finger.
Okay. Yeah.
So I want to try some like fine gauge wire because that'll maybe bend smaller and be stronger, but I don't know.
Like I guess that like it seems to me that your limitation is that you need a wire that's like strong enough to prevent it from bending sideways. Is that what I'm understanding here?
It needs to be strong, but also willing to make 90-degree turns. There's no 3D-ness to these parts in essence. They're 13 millimeters thick, and they're a 2D profile. And that's not true. There's the one hole on the bottom that the tendons run through. That's running sideways. But and that's really nice because it's incredibly easy to print parts like that. But the trouble is that I have this hole that the string goes through, and then there's a right angle to go out sideways. And
Okay.
if I use thicker string, that doesn't end up a right angle. It ends up a kind of small arc, and the string doesn't quite hug up against the wall of the part. And then when you put load on it, like more load, it hugs up a little bit more, and in the process, the finger bends sideways in a way that you don't want.
Oh, okay. Makes sense.
Yeah.
Yeah, that's all really interesting. Do you have
Sounds
any
great.
response about that?
It sounds really interesting.
Yeah. So, like, I guess, like, if you have time, I have a couple stuff that I've been working on, and it'd be great to hear what you think about it.
I don't have to pile in the car yet. Shoot.
Awesome. So, first thing I wanted is, so a couple folks at a Shriners Hospital have been talking about how, like, it's a natural orientation of the hand when you, for example, like when you, like ride a bike, right? You don't ride a bike like this. You ride a bike with your wrist flexed upwards, and then your fingers closed. So they wanted me to design a hand which would close when the wrist is flexed upwards. And so basically the design, I mean, again, this is like the simplest way possible, but basically thought of like flipping the gauntlet to the other side, and then like running the wires into, so from the top to the bottom. And I'm not explaining well over here. You can kind of see what's going on here. So you have this wire. Can you see what I'm showing?
Kind of. It's a little bit blacked out on the side facing me, but I can see the strings.
You want to start with the knot at the top?
Yeah.
Yeah.
Okay.
This is where it starts, right?
Yeah. So like the string will go from here. It'll go under and it'll curve on top of the palm. So like it goes from the bottom of the palm to the top. And then, there's my camera. Okay. And then like it'll go along the top of the palm and then go into like one of the side pilot holes. And then it'll come back out on the bottom. And so basically it was a way for me to like route the string through the existing hand design, and then I could tie it off on a gauntlet, which is on the bottom of the forearm instead of the top. Then you can just pull the string, and then you end up flexing your hands. Although I've noticed that it is a little bit harder to pull now because like it's routing through so many different turns.
Yep. So
we're still working on proof of concept.
Yeah.
Yeah. So I don't. This is just like a thing I try to maintain with all the wrist powered stuff. I like to keep this spot clear because I think there's a lot of situations where you end up kind of resting that part of your hand on something. And I don't know, I feel like the feedback's important. So when I saw that thread pop up on the group, I think it was, my thought was either do pushers like, so you know how Peregrine Hawthorne has these thick nylon cables that he uses he does this to close, but then he doesn't have elastics. He just unbends and the things push his fingers straight. So I think you could maybe take that further and do pushers on here on the tops of the fingers. So you bend like this, they get pushed up into the hand, and they close like that because they're pushing on the top sides of the joints. That might be kind of tricky though. And then the other thing you could maybe do is one really big pusher on the from the top of the gauntlet to the top of the thing that's pushing back, just like it's basically pushing the tensioner back, and then you run the actual drive cables through a little Bowden through this joint. So the actual drive cables aren't affected when you bend this joint, but their anchor point gets pushed backwards somehow.
Yeah, and the Bowden tube, like a Teflon tube, is one of the we're hoping to decrease friction right now. And I think we are kind of trying to focus more on with this current design is can we get it moving freely and how simplified do we have to get the routing. We were also doing the thought there a routing, maybe a serpentine routing on the back of the palm and the front of the palm would allow it to flex both ways. I don't know if that is possible, but that would be kind of interesting too. There's a way to route the wire.
Yeah. Oh, so
That's it. You would still be contracting. Anything out of straight would be flexed.
there should totally be a mechanism that you can put on the sides of the wrist that pulls when you bend either direction. I can't think what it would be right now, but that's totally a thing that you can make.
Yeah, so it's one of the ways we're trying to think about extending this to be not a complete change for people, but it would be an added function. They could have the normal thing they're used to, but also they could have it flex the backwards way. So the way that Gloria described it is that your power, they call it the power grip. It is actually about 5 or 10 degrees backwards from your arm, not forwards. So where all your power comes from, and that would be a better way to do it.
Yeah, totally.
Okay, we hadn't thought about side routing, so maybe if you go, if this routing doesn't work, to test it, then maybe there's a different way you can route it.
Yeah. Or I think the next idea with the pushers. So Nick, could you elaborate on like what sort of materials would comprises like a pusher? So the first thing I think of is like a compression spring, but is there any other materials that act like that?
I think that Peregrine uses weed whacker cable actually. So weed whacker, it spins a little plastic cable and chops grass over. You know those things? Yeah. I think he actually uses the nylon cord that they use for like the chopping blade as cabling, and he and that's like stiff enough that it pushes itself back through the joints.
Oh, I see.
And so you're saying that Peregrine has his tensioner on the top of the forearm, but he just uses pushers so that like when he extends back, it closes?
No, it's normal. It's still forward to close. It's still this.
Okay.
But normally we have like rubber bands on the back to open it when you unbend, and he doesn't have those. He just has these thick cables running through the bottoms. So when he unbends, those thick cables get pushed in, and they push the bottoms back open.
Oh, okay.
So they're routed on the front of the fingers.
Yeah, they're still on the front of the fingers. Yeah.
Okay, that's interesting. Yeah. We can explore that too.
Yeah. And we can look at if you want to look at some of his designs.
Yeah.
Peregrine.
So, do you know where Peregrine puts his designs? Is it all on the e-NABLE forums and stuff?
It should be, and he's really easy to get a hold of.
Okay,
just on Google Plus.
I'll definitely hit him up then. That's a good one. And so the next thing I want to talk about is the thumb redesign. So basically, I know and this has been a popular subject recently, but having a more opposable thumb. So I designed this. It's a good angle. So basically, how? And it works.
Go ahead.
It closes, so I have to pull it to close. There you go. Yeah, I think when I printed it, I didn't really clean it up, but yeah, so it works in the same way. And the only difference is that when you print, you have to print like vertically now. And like I was wondering what you had like your thoughts about that.
I think that's about the right angle to put a thumb at. What do you mean you have to print vertically?
So because if you look closely,
because it's sticking off the front. Yeah. So when I was looking at doing those thumb angles, I was thinking of a screw-on part to avoid that printing vertically.
Okay.
Or even just the other thing you can do is you can just do one that snaps in reasonably tightly, and then just take a soldering iron that you don't care about or a wood burning iron and just melt the parts together a bit.
That's good. Yeah, we had
like that's how I.
Yeah, the my kind of feedback on that is like, yeah, we definitely want, if the design works, we want a lot of people to be able to use it. And so we were saying that it would have to be a vertical print. Not everyone would be able to print it per se. But you know, as we talked about last summer, we want to do feasibility first. Is this a design that works, that works people like, that the doctors think are good? And if so, there's ways we can then modify it so that it's easier for other people. So the screw-on idea, the on idea, or the melt-on idea, those are really good points to make that we can think about.
And the last, yeah, go ahead.
Yeah, I'm also wondering if, with my my slidey joints that I've been posting about, if you couldn't print a sliding spot right here with the printed palm down. Seems, oh no, you can't. You need the sliding joints to be printed like axis of rotation on the z-axis. If you have layer lines on there, they're really rough and not fun to use. Never mind.
Another idea that I was thinking of is you could still print it flat if you just extrude the sides of the palm so that it comes out, it arches up the finger joint. And so it would look similar to with the flexi hand is designed.
Yeah, you can do that.
Yeah, that's another option. But yeah, like again, as Jordan said, it's more of a optimization issue than a feasibility one. And the last thing I've been working on recently is creating a mechanism so that way when you close, your hands get locked in that position. And so
please.
Yeah, because like the doctors have all been saying that patients have trouble holding on to things because the object wants to push your hand apart. And so if you just have a way for your hand to lock, then it'll increase the grip strength of the patient, right?
You know, one of the other challenges is because a lot of these kids haven't really strengthened those muscles for a while because they haven't do these motions with their hand. It might be an assistive technology if there's a way for us to help lock it in position where they can just actuate it once. It will stay holding the object whenever they move their hand, and then they can do something else.
So the way, I mean, the first idea that popped into my head was like a ratchet and pawl system. So I'm actually going to show you on screencast. I have a design printed out with me, but it's hard to show.
That first.
Okay.
The black and
can you see? Okay, yeah. So hold on, let me just. Okay, can you see this?
Yeah, totally.
So this is like, yeah. So this is a ratchet and pawl system. How I designed it is that like you have a cord going from here onto the palm, and so like when the palm is flexed, right, the distance on this thing increases, and so this goes upward, spins the ratchet, and the ratchet will want, and on the other end of the vertical line, there's going to be like a rubber band or string or something that will then in turn become flexed when this is pushed back. And so like the rubber band will want to push this vertical segment back down, but it can't because that's fighting against the ratchet. Yeah, I'll just show you this.
And then how do you release?
So release is actually I'll show you on here. So like release is going to be like whenever you release the pawl, then whenever you like release the pawl outwards, then the ratchet can then the vertical segment can move back down into its slot. But it just seems like, I don't know, the way that I'm thinking of it, it seems like a complicated solution to something that could be solved by other means.
Yeah, so I mean the simplest answer is to just grab your cables. So just flex, my cables are pulled, clamp them right here, and then it doesn't matter what my wrist does because my cables are still clamped, and then unclamp them somehow. When I was talking to Debbie Leong about this, I think it was, Sorry, I keep putting my hand in front of my mouth. You probably can't hear me. She was suggesting, I'm not sure how you would use this for a clamp, but it sounded like a good idea to me, using a sort of pen clicker mechanism where, so you...
Yeah, that's what we're talking.
Yeah, so you...
I also this is perfect.
You bend your hand, it grabs, and then you can go backwards, and it stays grabbed. And to release, you need to move forwards again, any amount. So,
okay.
So you grab, and then you're relaxed.
Have you ever taken apart a clickable?
Yeah.
It actually has.
I only sort of get how they work, actually, though. I looked at the parts, and I was just like, what?
It's a circular ratchet that spins.
Yeah.
And has 1 or 2 states.
Yeah.
So, like, returning to what you said about the clamping thing, we talked to Adam last week, and he said that he had like a slide latch system for crimping the cables.
Oh yeah, he does. Mm-hmm.
Yeah. So, I was hoping to ask him today, but it seems like you know a lot about it too. So, do you think you can elaborate?
I don't remember how his works. I don't remember how he's done it, but what does he do? Yeah, I'm really not sure.
This is saying that the crimping is not super reliable. Was that it?
Yeah, the crimping wasn't because you had 5 cables, but if you use like a Whipple tree, then you only have 1 cable in the end.
Yeah, that's a good idea.
One of our more stretch goals of trying to figure out, is there a workable locking mechanism that would be worthwhile to use, and we could test it out this summer.
Yeah, I really, really like locking. One of my other motivations for the fluid muscles thing to use hydraulics is because water is incompressible. So you fill one of these muscles and then you close the valve, and it can't.
Oh, you're kind of cutting it now.
I'm cutting out.
Yeah.
Hello?
Could you just repeat?
Am I back to normal now?
Kind of.
Mostly.
With the water muscles, if you fill one and then close the valve to it, it stays flexed. So that's kind of a very easy way to locking that I really like. So that was just one of my motivations to use water as opposed to air, because air would still be stretchy.
Right. Yeah. Yeah. So like this is all really useful. So yeah, have you encountered any like mechanisms for clamping that we could talk about?
Not really. I vaguely remember people doing this stuff a long time ago, and they found one of the best ways to clamp a cable with printed parts is just to have a sort of sawtooth pattern and put the cable right through here and go like this. So you end up forcing it into this really long serpentine motion. And
I think you were cut out for a second.
Do you want to try hiding your video camera? Maybe that'll up the bandwidth for your audio.
Yeah, I can give it a try. Is that better? Maybe.
Yeah.
It seems odd that. No. Yeah, I don't think it's my end actually.
Like I'll try like hiding ours. Just so.
Sure.
Yeah, my internet should be pretty okay here.
Okay. All right, turn camera off. All right.
Still good? Better? Worse?
No, it's actually lagging again. When you audio.
Well, I wonder if I can draw a picture or something. So.
Slower, maybe. That'll help.
Huh?
Okay. It's okay.
Am I smooth now?
Yeah.
Yeah.
Okay. Awesome. So the thing that I saw was basically you have 2 zigzag patterns, and you clamp your string between them. So your string has to make this S wave pattern, and it's just really hard to pull through, and it seems to work.
Oh yeah.
Yeah, and the other thing that's nice about doing that.
Yeah.
Oh, cutting out.
It's like a cleat on a boat.
Yeah, exactly. And the other nice trick about that is if you clamp the back of it first, pushing the cable into that serpentine pattern will also contract it a tiny bit further.
Yeah.
So if your like trigger my clamp mechanism has a bit of play in it, like backlash, this will eat that backlash up, and you could hopefully like make your teeth taller to kind of compensate for that as you feel appropriate.
Yeah, this is a good idea. I think we should go with clamps.
Yeah, that's really interesting. And I like it that if it does increase the length, it actually would be a mechanical assist for closing.
Yeah.
Oh,
because
yeah, that's interesting.
Yeah, that's really cool. Because one of the things we've been looking at is there a way to do a mechanical assist hand where small changes translate into large amounts of force, kind of like those. Have you ever used one of those easy staplers where they have a lot of tension springs inside that a little bit of force causes a huge release of energy? So we're thinking about that, but we don't want to weigh it down as heavy as a stapler, of course. So. All right, cool.
All right, yeah. This has been awesome. I got a lot of feedback. Yeah. Was there anything else you wanted to talk about, Nick?
No, I think I covered all my projects.
All right. Yeah.
Okay, cool.
Yeah.
In that case, yeah.
I probably have to go soon.
We're going to have these every week. So I'll see you again next week, I guess.
Yeah, see you in a week. Yeah.
All right, man.
I'll be sure to have lunch at this time.
Yeah.
Awesome.
Yeah.
Take it easy, Nick.
All right, Nick.
Bye.
Bye.